Let's take a look together at our problems on the practice test here. Number one, what I'm really trying to make sure that you understand is that whenever you have algebra that needs to be done inside of an integral problem, that you must do those algebraic operations first. So if any algebra can be done, it should be done first. Here I have two binomial expressions that I need to FOIL out before I carry out any integration. Now, please don't just think it's just multiplication. If I were to have a three-term expression divided by one term, the first thing you would do is you would distribute that denominator into each term in the numerator before you carried out any integration. So any algebraic simplification that can be done should be done. So in this case, I can just distribute the 5x through this group and I'll get 10x to the negative 1 plus 5x to the fourth. When I distribute through the negative 4, I will get minus 8x to the negative 2 and minus 4x cubed. Now at that point, for the three terms at the end, those are just going to be easy power rule integrals. The first term you need to remember is the exception to the power rule. If you tried to use the power rule on it, it becomes obvious because you'd say, well, if I increase the exponent by 1, it's 0, and I know I can't divide by 0. That should automatically tell you, oh, no power rule on that one. This is better looked at as 10 times 1 over x, and you know that the integral of 1 over x is the natural log of the absolute value of x, since we can take the derivative of the natural log and get 1 over x. So the first term gives me 10 natural log of the absolute value of x plus next term. If that goes to a 5 when I increase the exponent, then I need to divide by 5, which just cancels out the coefficient, and I have plus x to the fifth for the second. The third term, you say, well, if I add 1 to that exponent, it's going to become the negative 1 power. If I divide by negative 1, that's going to make that a plus 8. And then x to the negative 1, it's better written as x to the positive 1 in the denominator. So plus 8 over x is your best answer for the third term. Fourth term becomes easy because we know when we increase the exponent by 1 to x to the fourth, then you need to divide the coefficient by 4. 4 over 4 is 1, so we have minus 1 x to the fourth, or just minus x to the fourth. And then please remember, you always have to add in your constant of integration. For the next problem here, I asked you to approximate the area under the curve from 2 to 10, under the curve x cubed from 2 to 10. And I can say, in order to do that, what I'll go ahead and say here is to use the left-hand approximation. And I know if it has 4 rectangles, then the width of each rectangle, you'd say, well, it's the width of the entire region that you have to evaluate. End point minus beginning point, 10 minus 2, divided by the number of rectangles. Well, L4 has 4 rectangles. So the width of each rectangle is going to be the total change in x of 8 divided by 4. Well, the width of each rectangle is 2. Now, I take that common width of 2 and say the L4 approximation for this curve will be the common width of each rectangle times the height of each corresponding rectangle. Now, remember those heights, they're determined by the left-hand side of each rectangle. So you'd say, well, your first rectangle is going to go from x equals 2 to x equals 4. Your second one's going to go from 4 to 6. Your third one's going to go from 6 to 8. And your fourth one is going to go from 8 to 10. Well, the left-hand side of each of those rectangles is at 2, 4, 6, and 8. So I find my height of the function at each of those x values. So I can say the common width times the summation of the heights, where my heights are at f of 2, f of 4, f of 6, and f of 8. Now again, keeping in mind that that last rectangle at f of 8 would cover all x values from 8 to 10, and I know that that's where my region ends at. So now, the functional values of each of these, you just plug these x values into your function. So you have 2 cubed plus 4 cubed plus 6 cubed plus 8 cubed. Now for our final answer, the left-hand approximation L4 is going to be 2 times, I know this is 8, this is 64, this is 216, this is 512. You multiply all those by that sum, you get a 1600 for the L4 approximation. Good answer. Now, for my next problem here, I'm asking for the infinite Riemann sum to represent the integral 0 to 6 of 2x squared minus 5x dx. You have your infinite Riemann sum formula given on the top of your sheet, and I just need to figure out how it applies to this function. And so you say, well, we know that A, it's just the beginning point of your region. So in this case, f of A, that's just f of 0. Now, delta x, just as in the last problem, it's the end point minus beginning point divided by the number of subdivisions. Same thing here. End point minus beginning point divided by the number of rectangles that's within it. This time there's going to be n rectangles as n goes to infinity. So the width of each rectangular region is going to be 6 over n, and I know that that's going to become infinitesimally small as n goes to infinity. But 6 over n is the expression that represents it. So now I go in and I start plugging things in. And please keep in mind, when you don't put indices on the summation, it's implied to be from 1 to n. So you can put it each time if you want, or you can drop it like I've done here, and it's implied to be from 1 to n. So I'll say my Riemann sum here is the limit as n approaches infinity, the summation from 1 to n of f of A, which is 0, plus delta x times I. That's going to be your 6 over n times I. I'll just call it 6i over n. That's all the part inside your function. That's where you're going to get the values of x to plug into your height formula in each one, just like these are my heights in my last problem. This is my height in this problem. Now, times the width of all of those heights. Well, each height has a width of 6 over n. Just as I did last time where I pulled that common width out in front, I'm going to pull that common width of 6 over n out in front of my summation of the heights. And also, just like last time where I said, well, what is f of 2? What is f of 4? And I had to plug it into the function. That's the same thing I do here. I say, well, what is f of 6i over n? You plug 6f of 6i over n into your function for x, and you'd say, well, that's going to become the summation of 2 times 6i over n squared minus 5 times 6i over n. Now, when I simplify out this formula for the heights, 6i over n is going to give me 36i squared over n squared. Multiply that by 2, you get 72i squared over n squared. Multiply 5 times 6i, you'll have minus 30i over n. All of this is my formula for the heights of each of my rectangles. Out here I have times my common width, and this is all still inside of a limit as n approaches infinity. Now at this point, I need some way to simplify these heights formulas. We know we have a summation formula for the summation of I squared, and the summation of I cubed. So I need to get these down to where that's the only thing inside the formula. I can do that by distributing this summation of the first term minus the second term. I can call that the summation of all the first terms minus the summation of the second terms, and make sure that 6 over n multiplies both of them. So I'm going to break this summation up into 2 individual summations. When I break up the first summation, the whole reason for breaking it up is that I would like to factor that 72 over n squared out. So you'll see that's precisely what I did. 6 over n times 72 over n squared times the summation of I squared. Then I have minus 6 over n times 30 over n is what I needed factored out of this second portion, times the summation of I. Then if you look, or hopefully you even know, the summation from 1 to n of I squared, it's equal to n times n plus 1 times 2n plus 1 all over 6. And the summation of I, as proven by Carl Gauss from 1 to n, it's equal to n times n plus 1 over 2. Now, all of this is inside of a limit as n approaches infinity. Both of these are rational functions, a polynomial divided by a polynomial. So what you're supposed to remember is in that situation, the only terms of relevance are the highest powered terms in the numerator and in the denominator. Every other term is infinitely times smaller than that leading term. So in order to show that, what I did to simplify out this first one is I know that over here I would get a 2n cubed times 432. 432 times 2n cubed is going to give me 864n cubed. Now I know that there's going to be an n squared, an n, and a constant term as well, but those terms are irrelevant. I show that by putting plus dot dot dot. That's just showing the viewer that yes, there's other terms in that numerator, but they have no significance to the answer. My denominator is the 6n cubed. I go to my second term. Now, of course, this one's easier to see. It would be 180n squared plus 180n. I don't need that 180n. I can just say it's 180n squared. I would have n to the second times 180 over 2n squared. Again, I put the plus dot 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 just to show that yes, there's other terms in the numerator, but they have no significance. Then for any rational function that has the same degree in the numerator and denominator, the limit as n approaches infinity is just the fraction of the leading coefficient. So the first term is 864 over 6, which reduces down to 144. Your second term, minus 180 over 2, reduces down to 90. 144 minus 90 is 54. Now, in a problem like this, and you'll notice I said in the directions, you need to show work for credit, because you could get this answer of 54 and I would give you no credit if I didn't see the infinite Riemann sum work in this problem. The reason for that is you could easily do this on your calculator here. I'll go ahead and show this here. It's the Math 9 feature on your calculator. If you hit Math and then 9, it brings up the integral for you. And what it would enable you to do is you could just say, well, I'm going to integrate from 0 to 6 of this function, and my function is 2x to the second minus 5x. We're evaluating this with respect to x. Now, please notice it's going to give us that answer of 54. And you're thinking, that's terrible. I don't want the calculator to give me the answer. And while I don't either, there are some good benefits to it. You can use it to check your work, but that is again why I'm saying a final answer is worth no credit without the supporting work. So yes, it would be wise for me to check this on the calculator to make sure I haven't, bungled my algebra and it led me to a wrong answer or something. But just putting 54 as your final answer without the gorgeous work of Riemann sum in between, not worth anything. Now, similar to the next problem, like if I wanted to go ahead and look at my number 4 before I show you the work and the answer, what if I wanted to do that one? I could go Math 9, I want to integrate from 0 to 5, and it's the absolute value. Best way to do absolute value is second 0, and it brings up the absolute value as the first one. And we have 3x minus 8, and I'm integrating this with respect to x. Boom. Now, it has a very slight rounding error on this one. It should be 18 and 5/6 here is what the answer should be. That should be 18.83 repeating. Now, in order to show where that answer really comes from, we'll do the work. And you say, well, when you do the work for an absolute value, the first thing you need to remember is that there is no such thing as the integral of an absolute value function. So we have to say, I'm going to have to look at what's inside of that absolute value and consider when it's positive and consider when it's negative. When it's positive, the absolute value does nothing. When it's negative, the absolute value is going to act as the negative of that group. So I set what's inside equal to 0, and I know that that's going to happen when 3x is 8, or at x is equal to 8/3. So what that tells me is that the absolute value of 3x minus 8, it's actually the negative of the group 3x minus 8 for any x value less than 8/3. And you can see that. You could easily plug in a 0 and say, well, at 0, this is -8. The absolute value is going to have to change the sign of that. But for any value greater than or equal to 8/3, then what's inside at 8/3, it would be 0, and the absolute value would do nothing. Anything to the right of 8/3, your 3x minus 8 is going to be positive, and your absolute value, again, is not going to do anything. So I can say for any value greater than or equal to 8/3, the absolute value of 3x minus 8 is just 3x minus 8. So then we can say, and this is the important thing, that you understand how this is set up. The integral from 0 to 5 of the absolute value of 3x minus 8 with respect to x is the negative of the integral of 3x minus 8 from 0, the starting point, up until 8/3. But then, starting at 8/3, going to our ending point at 5, I can just say, well, it's the integral of 3x minus 8. I don't have to change the sign. So I subtract the answer I get here. I know the answer I get to this first one, it's going to be a negative. It has to be, because my function is beneath the x-axis. That's why I'm going to subtract that portion. So now, when I integrate, integration is easy. It's just power rule. 3x squared over 2 minus 8x. That's evaluated from 0 to 8/3, and I get that same integral evaluated from 8/3 to 5 here. We know we're subtracting off our first region and we're adding our second region. Now, whenever you're evaluating this, it might be, again, and this you can certainly do. I don't need to know the arithmetic. Now, could you have fun with it and plug 8/3 in manually and say, well, that's 3 over 2 times 8/3 squared, which is going to be 64 over 9 minus 8 times 8 over 3, and then simplify those? You could. You could have fun with it. But that kind of might take some time, and it might open up a lot of chance for error. So it might be wiser to do it this way. I know I'm trying to plug 8/3 in for x, so I'm going to go ahead and say, well, 8 over 3, I'm going to store that in for x. And then I'll hit alpha decimal to bring in the colon. Alpha decimal brings in the colon there. And I'll type in my function, which is 3x squared over 2 minus 8x. I'll say 3x squared over 2 minus 8x. Now, I have my function entered in. I'm evaluating it at 8/3. It's going to give me this answer. Well, it's putting it in decimal format. I can hit math, enter, enter to change that to a fraction. So I know when I evaluate this group at 8/3, I get a negative 32 over 3. Second, the lower limit here, you don't have to worry about, because you know it's at 0. Any polynomial evaluated at 0 is 0. Now, again, please keep in mind, I said before I even started this problem, I knew this integral in this region would have to give me a negative, because it's always negative up until 8/3. Well, it sure did. The area under the curve is going to be negative 32 over 3. That's why we have the minus sign on the out front. That's going to, the absolute value is going to change that to a positive area. Now, for this second region, you would just say, well, I'm evaluating this same function at 5, so I could just hit second enter to bring back up this expression, and I'll go back and type a 5 over the 8/3, so I'll type in a 5, and I'll have to delete off those 2 digits. 5 stored in for x now, and I see a negative 2.5. Not that we don't already know it, that's negative 5 over 2, but if you wanted to convert that to a fraction, you could. So when I evaluate this expression at 5, I get negative 5 over 2. We already know when we evaluate it at 8/3, it's a negative 32 over 3. Please remember, it's top limit minus the lower limit. So you say, well, that's going to become minus a negative 32 over 3. So the way I thought about this is I'm just going to have positive 32 over 3 plus 32 over 3. That's going to give me 64 over 3. Then I have minus 5 over 2. That's going to give me a final answer of 113 over 6. Because of course, you have to get a common denominator there. It'd be 128 over 6 minus 15 over 6. Now, for number 5, we're looking at the difference between displacement and total distance traveled. I give you a velocity function of 17 minus 5t, and I say a particle moves at this velocity between 0 and 6 seconds. So then we're supposed to find the displacement and the total distance traveled. Well, the displacement, as the name would imply, it's simply change of placement. So if I move backwards 10 meters and then forwards 10 meters, my displacement is 0 because I'm at the exact same place I started at. So whenever we're trying to find the displacement, we simply just integrate from the beginning of time to the ending of the time of the particle of your velocity function with respect to time. Power rule is going to give me 17t minus 5t squared over 2. I'm evaluating this, and I really only need to evaluate it at 6, since at 0, it's going to be 0. When I evaluated at 6, I got 12 meters. So this told me that, assuming that moving to the right is a positive position in this problem, the particle is 12 meters to the right of its original position after 6 seconds. Now, that is not saying that the particle has moved a total, or sorry, all of 12 meters. That's just saying that's the change of placement of the particle 6 seconds later. But if I wanted to find the total distance traveled by the particle, then I need to say, well, then any distance traveled needs to be considered a positive distance, regardless of whether it's in a positive direction or a negative direction. In order to do that, we just need to take the absolute value of that velocity function, and then it becomes a problem very similar to our last one, where we say, okay, then that means you need to set what's inside that absolute value, your velocity function, equal to 0. We know that that velocity function is going to equal 0 when 17 is equal to 5t, which means t is equal to 17/5. So at 3.4 seconds, or at 17 over 5 seconds, this velocity function is 0. We know clearly at time 0, it starts off with an initial velocity of 17. So it starts off with a positive velocity, and it's only going to turn negative for values after 17 over 5. So I can say for the first 17 over 5 seconds, that absolute value does nothing. So you'll see the distance traveled is the integral from 0 to 17/5 of the velocity function, minus from 17/5 to 6, this function is always going to have a negative velocity, so that absolute value is going to have to change the sign. So I say minus the integral from 17/5 to 6 of this 17 minus 5t function. Again, when we integrate, it's just simple power rule. The evaluation, when I evaluated this group at 17 over 5, I got 28 over 9, of course, minus the lower limit of 0. And then when I evaluated the second group, and I was 100% sure that the answer to this second group, when I did top limit minus bottom limit, it would be a negative, and it was. When I plugged a 6 into that function, I had a 12. Of course, when I plugged the 17/5 into it, I had the minus 28 over 9. So this is saying in the final 6 minus 17 over 5, so in the final 13/5 seconds, you're actually traveling to the left 17.9 units. That's what this is telling us. But we need to account for that as a positive movement to account for the total distance traveled. That's why we're subtracting it. So we say the position moved in the first 17 over 5 seconds plus the position moved from 17 over 5 to 6, or minus, I should say, to make sure that we do add it. And you can say, well, that's 28.9 plus 16.9, and our total position traveled is 45.8 meters. Again, please keep in mind, this 16.9 right here just meant that it was really, if this was a position moved to the right, this was distance moved to the left, and then you say, oh, so my total displacement was still 12.9, but if I'm just talking about the total distance traveled, it's 45.8 meters. Pretty cool problem there. Now let's talk about the integration problems. Problems 6 through 14 are all techniques of substitution. Now that's quite a few substitution problems. You can see quite a bit of this test, like I only have one problem covering Riemann sums. Do I want you to know how to do Riemann sums? Sure. But as far as your ability to succeed in later classes, is it really dependent upon whether you understand the underlying logic of Riemann sums? Probably not. Will you have to understand how to do substitution in later classes? You bet. You can never forget these topics of substitution and move on to any future math class. It would haunt you forever. This is just something you have to be comfortable with. So if I look at a problem like number 6 here, and I have the integral of x on the cube root of 4x squared minus 5, and of course I need to integrate that. Well, I integrate it by letting what's inside the group to a power be my u value. So I can say, well, the innermost part of this function is the group 4x squared minus 5. If I let u equal 4x squared minus 5, then the derivative of u would be 8x to the first with respect to x. Now, in order to do this substitution, I have to see an 8x dx in that problem. I don't see it. I see a factor of x dx. So from this step to the next, I just made sure that this substitution was possible. I multiplied by 8 on the inside, and then I eliminated that multiplication by dividing by 8 on the outside. That wasn't too good, eliminate. So I can say, all right, multiply by 8 on the outside, divide by multiply by 8 on the inside, divide by 8 on the outside. Now, when I multiplied by that 8 on the inside, it made me, it enabled me to see, yes, this factor of 8x dx, that's going to become du in my next step. Well, then the rest, the only other thing in there is your cube root. And you know that what's inside of that cube root is called u. So this is going to become the cube root of u. Well, the cube root of u is more easily written as u to the 1/3 power. And now the reason I would write it that way is now I can just use the power rule. Please remember, the whole point of substitution is to take a problem that we cannot integrate with basic techniques and create a problem that we can integrate with basic techniques. So substitution has served its purpose. I now use the power rule. That's going to become u to the 4/3 and then times 3/4, which I have right there, plus our constant of integration. When I distribute through that 1/8 that I had on the outside, that's going to give me 3/32. And then this becomes the cube root of u, which is the cube root of 4x minus 5 raised to the 4th power in that numerator, plus your constant of integration. For number 7 here, it's very similar, slightly more difficult. You say, well, typically your choice for u is the innermost part of the integral. No question here, that's the group 3x plus 7, since it's inside the group to the 7th power. So I let u equal 3x plus 7. The derivative of 3x plus 7 would just be 1 with respect to x. So I get du is equal to dx. But now I see, yeah, I'll be able to replace dx with du. This is going to become u to the 7th. But I have this other factor of x that I'll have to take care of. The factor of 2 I'm not really worried about because I can always factor any constant to the outside. That's what I did there. But now this x, I can solve for it. If u is equal to 3 plus x, then x is going to equal u minus 3. That's what I do right here. So now that I get that that x is equal to u minus 3, I then substitute that in for x in my problem. Times the u to the 7th times du. At this point, sometimes students say, well, you're no better off than you were to begin with. We're infinitely times better off now than where we started, because where we started was with a problem that had no algebraic or simplification. You can't distribute this 2x throughout the group 3 plus x to the 7th. However, you can distribute u to the 7th throughout the wimpy linear function of u minus 3. So I distribute that through and I'll get u to the 8th minus 3u to the 7th. I'm integrating that with respect to u, which we know how to do because that's just power rule. You'll get u to the 9th over 9 minus 3u to the 8th over 8 plus your constant of integration. Final step here, I always need to get it back in terms of x, and I also distributed the 2 here, so I got 2/9, and then u to the 9th becomes the group 3 plus x to the 9th. Then I would have 2 times 3 over 8 gives me minus 3/4, and then u to the 8th becomes the group 3 plus x to the 8th plus your constant of integration. Final answer there. I'm not sure why I didn't circle it. Number 8 here. This one, slightly trickier. I could see a student saying, well, I'm not sure what to call u here, because you said typically you let u be what's inside something inside of a function. Well, there's two terms here. You could think of the secant being inside of the group squared. That'd be a terrible choice for you, though. And you think, well, why? Because if I'm thinking, well, what if I hypothetically let u equal the secant of x? Du would be secant x tangent x. Do you see a factor of secant x tangent x anywhere? Nope. Therefore, secant would be a poor choice for you. But then when I think of the denominator, I said, well, that denominator's technically a function inside of a function, because I could say, well, the function tangent x plus 4 is implied to be to the -1 power. So it's kind of an inside of a function. So I let that be u. And I say, is that a good choice for you? You bet. Because then I can say the derivative of tangent is secant squared x dx. Of course, derivative of 4 is 0. So I get du is secant squared x dx. Now, I have the secant squared x dx already up there, so that's going to become du in the next step. That negative factor, I just bring to the outside. So it's the negative of the integral 1 over u du. And I know I can integrate 1 over u by just saying it's the natural log of the absolute value of u plus the constant of integration. We have all of this multiplied by a negative. So then you can say, well, then my answer is going to be the negative of the natural log of u is equal to tangent x plus 4 plus our constant of integration. Please remember, it would not be wise to say, well, can I say a minus c? Well, it'd be better not to. It's technically not wrong. You can say plus c or minus c, but c automatically has to stand for every number in existence, positive and negative anyway. So it's best format to always just say plus c. For number 9 here, we have the integral from pi over 6 to pi over 4 of cosine cubed x times the sine of x with respect to x. So for this problem, u is the function inside of a function. Cosine is inside of a group to the 3rd power. So I'll let u equal cosine x. Well, the derivative of cosine of x is the negative sine of x with respect to x. So the first thing I had to do here was say, I don't have a factor of negative sine x dx. I need to multiply by a negative on the inside, and in order to make up for that, I'll multiply by a negative on the outside. That's what I've done here. This negative sine x dx can all become du, and then my cosine cubed can become u cubed. But what I also had to do from this step to this step, in this step, everything was still in terms of x. So these limits of integration are also with respect to x. But when I change to u, my limits of integration need to change to u. So that's what I did down here. I need to say, well, these limits, because this is with respect to x, this is from x equals pi over 6 to x equals pi over 2. So if I want those limits to be from u equals from something to something, then I need to change my limits of integration. U evaluated at the lower limit, pi over 6, would give me the cosine of pi over 6. Cosine at pi over 6 is the square root of 3 over 2. At the upper limit, you're just evaluating the cosine at pi over 4, which is the square root of 2 over 2. So now I changed my limits of integration. That enabled me to now to just integrate this with the power rule and get u to the 4th over 4. Please don't forget your negative out in front. And then we're evaluating that from square root of 3 over 2 up to the square root of 2 over 2. Now, I just did this in my head. I said, well, if you plug square root of 2 over 2 into u to the 4th, the square root of 2 to the 4th is going to be, I know that the square root of 2 times the square root of 2 is 2. So I'm going to have 2 times 2. My numerator is going to be 4. My denominator would be 2 to the 4th would be 16. 4 over 16, which would reduce down to 1/4, but then I'm dividing by 4. That gave me 1/16. My second one here, you'd say, Well, your numerator is going to be the square root of 3 over 2 to the 4th. The square root of 3 to the 4th, that's like saying 3 times 3 is 9, because we know the square root of 3 squared is 3. So I'll get 3 times 3 is 9 for my numerator. My denominator, again, would be 2 to the 4th, 16. So that's 9 over 16 divided by 4 gives me 9 over 64. And then 1/16 minus 9 over 64 would be 4 over 64 minus 9 over 64 for a negative 5 over 64. And of course, we're changing the sign to a positive 5 over 64. Now, for the next integration problem, number 10. So again, we're still dealing with substitution. I give you a quotient in there, but there's no way to algebraically simplify that quotient. So we just say, let's let u equal the denominator. If I let u equal t plus 7, then derivative of u is going to be dt. So obviously, I know that the substitution is possible since du is just dt. I can substitute those two out. But before I do that substitution, I need to think of what my numerator is going to become. My numerator is t plus 1. I know that u is equal to t plus 7. So what I did is I said, well, wouldn't it be nice if I could just solve for the whole term in that numerator? I can. All I have to do is subtract 6 on both sides of this equation. U minus 6 would equal t plus 1. So now that numerator t plus 1 gets replaced with u minus 6. My denominator is u. dt is du. I also changed the limits of integration. I actually evaluated the upper limit first. U evaluated at 2 is just 2 plus 7, or 9. My lower limit is going to be u evaluated at negative 4. Negative 4 plus 7 would give me 3. So I'm integrating from 3 to 9 of this function. Are we in better shape here? Absolutely. Because now, if you have a polynomial divided by a monomial, that monomial can and should distribute into every term in that polynomial. So you'll get u over u. That's just 1. Minus 6 over u. And I can say, oh, that's the same thing as 6u to the negative 1. That's going to integrate to be 6 natural log of u. Gorgeous. So now, when I integrate the first term, integral of 1 with respect to u is just u. The integral of 6 over u is 6 natural log of u. So I get u minus the 6 natural log of u, evaluated from 3 to 9. When you plug in the top limit, you'll get 9 minus 6 natural log of 9. Evaluate the bottom limit, which we know we're subtracting, you'll get 3 minus 6 natural log of 3. Now when I simplify, the constants combine. 9 minus 6 is 6. Then I'll have minus 6 natural log of 9 plus 6 natural log of 3. So then you could have left it like that, but I just saw, hey, I could condense these two logarithmic functions down. A minus logarithm just means that that term is in the denominator, and I can say this is 6 plus 6 natural log of 3 over 9. And then I thought, well, this would be an okay answer as well. But then 3 over 9, that's the same thing as 1/3. 1/3 is the same thing as 3 to the negative 1 power. That exponent can come down and multiply the front, and I would have 6 minus 6 natural log of 3. Now, did you need to do the arithmetic to simplify to that? No, it's cool if you do, but it's okay if you don't. I'd have been all right with that answer. This answer is just slightly better. Now, for 11, I wanted to do a problem in which you didn't have to do the substitution. You could. So if you wanted to let u equal x plus 3 on number 11, certainly, that would be a fine step. But anytime you have a linear function to a power, remember, substitution's not necessary there. I can just say the integral of any linear function to a power, I can just use the power rule on that entire linear function. Now, what I do have to remember is that if x had a coefficient, I would have had to divide by the derivative of what's inside in this step when I integrated. But in this case, that wasn't even applicable. If I'm integrating from 1 to 6 of x plus 3 to the 1/2 power, I just say, well, power rule says that this is equal to x plus 3 to the 1 greater power, 3 over 2 power, then divided by that new exponent, which means I multiply by 2/3. Now I'm evaluating this from 1 to 6. If I plug in a 6, I would get 9 to the 3 over 2 power. That's going to give me the square root of 9, which is 3. And then 3 cubed would be 27. I would get 27 times 2/3. That's going to be 54 over 3, which I've reduced down to 18 there. Minus your lower limit, when you plug a 1 in here, you would get 4 to the 3 over 2. That means the square root of 4, which is 2. And then you're cubing that. 2 cubed is 8. It'd be 2/3 times 8, which is 16/3. 18 minus 16/3 is going to give you 38 over 3 for your final answer there. Next problem, I'm wanting you to remember every single solitary time you see a constant divided by a quadratic, you should be highly suspect that, hey, there's an inverse tangent going on here. So when I see 3 divided by 9 plus 4x squared, I'm thinking, well, I know 1 over 1 plus x squared is the inverse tangent of x. This is going to be something similar to that. To see that, I would highly suggest factoring it out to try to make it look as close to 1 over 1 plus x squared as possible. So I'm going to factor a 3 out of the numerator, and I'm going to factor a 9 out of the denominator. When I do that, I'm left with 1 over 1 plus, and remember that 9 factors out of both terms in the denominator, so you have 4/9 x squared for your second term down there. All of this integrated with respect to x. Now, at this point, you might say, well, that's still not the inverse tangent of x, and it's not. But I know if I could write this as 1 over 1 plus u squared du, then it's the inverse tangent of u. So that's precisely what I want to do. So I'm going to let u squared equal this 4/9 x squared. Now, if u squared is equal to that, then I can take the square root of both sides, and u is going to equal 2/3 x. Which means the derivative of u would be 2/3 dx. Now, I need to see a 2/3 dx inside my problem, and I don't see it. So I go to the inside and multiply by 2/3. I can do that if and only if I do the opposite on the outside. Please notice I multiplied by 3 over 2 on the outside. Now, this 2/3 dx, all of that's going to become du in my next step. 1 over 1 plus 4/9 x squared, it's going to become 1 over 1 plus u squared. And again, the whole point of substitution is to take something that's not in standard form, where you can use basic rules, to create something that is in standard form and you can use basic rules. By definition, the integral of 1 over 1 plus u squared is the inverse tangent of u. So I'm going to get, and keep in mind, my coefficient here, I had 1/3 times 3 over 2. That gave me 1/2. I'll get 1/2 inverse tangent of u plus the constant of integration. And then I can say, well, u is just equal to 2/3 x, which inside of the inverse tangent function, I think it looks better to write that as 2x over 3. So I get my final answer there. For 13, you have the integral of, remember, that's an understood 1 with that dx up there. The integral of 1 over the square root of 25 minus 16x squared integrated with respect to x. Every single solitary time you see something in the format, a constant divided by the square root of a constant minus a variable squared, you're supposed to be thinking, oh, this is some type of inverse sine function. How do I get to that? Well, I know that that 1 over the square root of 1 minus x squared is the inverse sine of x. I need to get this to look as much like that as possible. I already have the factor of 1 in the numerator, so that's not a problem. But I need this to be the square root of 1 minus a variable squared in there. So I need to divide the denominator by the square root of 25. I do that by factoring out the square root of 25, and then I factor it all the way to the outside, and my coefficient on the outside is going to be 1 over the root of 25. Now, if you factor that root of 25 out of this, then you're going in there and you're dividing both of these terms by 25. So you get the square root of 1 minus 16/25 x squared. And then it's very similar to the last problem, and you say, well, in order for this to be the inverse sine, this needs to be the square root of 1 minus a variable squared. I'm going to let that be u squared. So I'll let u squared equal 16/25 x squared. That means u is going to equal 4/5 x when we take the square root, take the derivative, and du is just 4/5 dx. Now, I don't see a 4/5 dx in there. I just see a dx. So notice in this step, I multiplied by 4/5 on the inside, did the opposite, multiplied by 5/4 on the outside. This is the equivalency. You're just saying, oh, I'm multiplying by an understood 1, which is a legal maneuver. Now, this 4/5 on the inside, all of that's, sorry, this 4/5 dx is going to become du. So I get du in that numerator. Remember, it's the same thing as du out the side of it. Doesn't matter. And in my denominator, I'll get the square root of 1 minus u squared. By definition, that integral is the inverse sine of u. I'll keep my coefficient of 1/4 after I simplify with it, 1/4 inverse sine of u. After I plug back in, I know u is equal to 4x over 5. I'll get 1/4 inverse sine of 4x over 5 plus your constant of integration. Now for the last problem that I'll do in this video, I'll do another video with the remaining problems. For 14, I'm wanting you to see that when it's necessary to break up the terms inside of an integral. Anytime you have a polynomial in the numerator, technically for however many terms you have, you could create that many separate integral problems. Now the reason it's necessary here is if you look at that denominator and say, could I let u equal x squared plus 16? You say, no. Why no? Well, because if I did, du would be 2x dx. Look at that numerator. Could you ever get a factor of 2x in that numerator? You say, no, because the linear function 2 minus 3x is not factorable. Then that means you have to break it apart. And so I'll say, all right, then I'll have the integral of 2 over that denominator integrated with respect to x minus, now I went ahead and factored that 3 out front. And the reason I did so is because I was thinking I need a factor of 2x, not 3x. Well, then let's pull that 3 out front and I'll have the x dx over the x squared plus 16. Now, as I go in and I start integrating these, I'll have really 2 separate problems within this one problem. My first problem, my second problem. My first problem, I need to be thinking of it as, well, it's very similar to number 12. It's a constant over a variable squared. Isn't this going to be an inverse tangent function? Oh, you bet it would be. Now remember, an inverse tangent is 1 over x squared plus 1. So you say, well, then I need this to be a 1. I need this to be a 1. I'm going to factor out a 2 over 16. Factor the 2 out of the numerator, the 16 out of the denominator. That'll give me a numerator. I can put the dx up there. My denominator, 16 divides into both terms, and you'll have 1/16 x squared plus 1 when it divides into both terms. At this point, it's more obvious that it's an inverse tangent function, but you're not quite there yet because I need that first term just to be u squared. I let u squared equal 1/16 x squared. That means u is going to equal 1/4 x. And then the derivative of that would be 1/4 dx. So now, and let me go ahead and finish this first one, then I'll talk about the second one. What I did from here to here is I said, I need to see a 1/4 dx in there. I'll multiply by my numerator by 1/4, but I need to make up for that by saying, we'll do the opposite on the outside. If I multiply by 1/4 on the inside, I multiply by 4 over 1 on the outside. Again, this is multiplying by an understood 1, legal maneuver. Now on the outside, that 4 and the 1 over 8 that was already out there from the 2/16 are going to multiply to give me 1/2. On the inside, this 1/4 dx is going to become du. And my denominator, the whole reason for doing this substitution is so that I could write it as u squared plus 1. Now we know the integral of 1 over u squared plus 1 by definition is the inverse tangent of u. So I can go from here to here in one step and just say I have 1/2 inverse tangent of u. And now I know u is equal to x over 4. So this is going to be 1/2 inverse tangent of x over 4. That's the first part of my answer. The second part of my answer comes from this one, which remember came from this right here. I already knew that if I let a variable equal that denominator for substitution, I needed my numerator to be the derivative of the denominator. So you'll see in this step, I went ahead and said, let's multiply that numerator by 2 and divide by 2 on the outside. That enabled me to say, and please, whenever you're using two different substitution variables, don't call them both u. Since I called the first one u, I'm calling the second one t. You could also call it w. That's frequently used. I'm going to call this one t, though, and if I let t equal x squared plus 16, dt is going to be 2x dx. Now I already have that 2x dx right there, so that's going to become dt in the next step. So then the only thing I have is 1 over t dt multiplied by this minus 3 over 2 in front. And then I can say, well, by definition, this is just the natural log of the absolute value of t plus my constant of integration. When I substitute back in, I know t is x squared plus 16. Since x squared plus 16 is guaranteed to be positive, I just was saying here, I don't need the absolute value. There's no point in it. And I got to my final answer of 1/2 inverse tangent of x over 4 minus 3 over 2, natural log of x squared plus 16 plus your constant of integration. All right, now, if you need help on any of the remaining problems, please keep in mind, I'll do a second video for that. These Zoom videos that I'm recording tend to mess up if I try to record any more than an hour at a time on one video. So that'll be done on another recording.